Hello everyone and welcome back. I am Mr. Cobalt and today I'm going to be going over oxidation reduction reactions, but I'm going to be focusing on oxidation states and the rules for assigning oxidation states to various elements or atoms in a compound. So this is going to be very important for you to use to be able to identify whether you have an oxidation reduction reaction, because you're going to be looking for a change in the oxidation states. If there's a change in the oxidation state, then that means that there was a transfer of an electrons. Now let me just explain what we mean by an oxidation state. An oxidation state is not a real charge. It's kind of a hypothetical charge where we assume that the electrons that are being shared between two atoms, that those electrons in the shared bond, would go to the atom that has a more desire, and that's not the right word, but an attraction for the electrons. So, for example, if you have chlorine and hydrogen bonded together, then the way that the scheme that is used to determine the charge, or I should say the charge on the elements, is that you assume that here that we have two electrons in the bond. Since chlorine wants the electrons more, it's going to attract the electrons more. So we would just give the two electrons in the bond to chlorine, and no electrons would go to the hydrogen. So there wouldn't be an equal sharing of the electrons. Okay, so then if that's the case, then this would give a negative oxidation state of 1, and a positive oxidation state of 1 to hydrogen. If there was equal sharing of the electrons, then each one would get 1, and then they would both be neutral. But the scheme that is being used to figure out oxidation states is to give all of the electrons in the bond to the element that wants them more. Okay, so in that case, I want to point out the fact that when we write oxidation states, the way we write out oxidation states is the opposite of the way we write down charge. So you may have noticed that I have a tendency, if I'm writing charge, so for example, oxygen tends to have a 2 negative charge. The negative follows the 2 in the charge on the ion. So when we're talking about ion charge, the negative and positive follows the number. When we're talking about the oxidation states or oxidation numbers of atoms in a compound, then the charge comes before the number. So this is the way we write formal charges. This is the way we write not formal charge. Sorry. This is the way we write oxidation states. This is the way that we write the charges on our ions. So I just want to point that out too. So here are the rules for assigning oxidation states. And these are in order of preference. So rule number 1 takes preference or precedence over rule number 2. And rule number 2 takes precedence over 3 and 4 and 5. So, and then 5 I'll get to in a minute with this table. So the first rule is that atoms that are in a free element, they're going to have 0 oxidation state. So any elements that are by themselves in their standard state, that's going to be 0. So for example, if you have metal that's solid, copper solid, that's a free element, that's going to have a 0 oxidation state. Chlorine gas, this is an element. It's the standard state of chlorine is Cl2 gas, so that's going to be a 0 oxidation state as well. So all atoms in a free element have an oxidation state of 0. Number 2, monatomic or monoatomic ions. Those are ions that are one atom with a charge. the oxidation state is going to be the same as their charge. So if you have a monatomic ion by itself, it's not part of a compound, it's just by itself, then the oxidation state of that ion is the same as the charge on that ion. So here I have a free calcium ion, says 2+ charge, so the +2 oxidation state. For chloride ion, I have a 1 negative charge, and so the oxidation state is -1. Number 3, if you have a molecule or a polyatomic ion, right? So an ion that is made up of more than one atom or element, and that has a charge, then the total number of the oxidation states. So if you sum up the oxidation states of all the atoms in the molecule or the polyatomic ion, then those oxidation states should total, the sum of them should equal the charge on the molecule or ion, right? So if it's a molecule, it's going to have no charge. So the overall charge on a molecule is 0, right? So if you're figuring out the oxidation states, then the oxidation states for the hydrogen, the 2 hydrogens, and the 1 oxygen should equal 0 because there's no charge on the water molecule. For this polyatomic ion nitrate, the 1 nitrogen and the 3 oxygens, the oxidation states for the 1 nitrogen and the 3 oxygens, should total to the same charge, which is a -1. So the oxidation states should sum up to the charge on the ion, or 0 if it's a molecule. So that's number 3. Number 4, if you are in a compound. So in compounds, metals have positive oxidation states. So this is always the case. So for example, group 1A and group 2A. Group 1A are always going to have +1 charges in a compound. So if they're in a compound, group 1A elements are always +1. So we have sodium chloride, so sodium is a +1 oxidation state. Group 2 elements are always a +2, a +2 oxidation state. So calcium in this compound with calcium fluoride, calcium has an oxidation state of +2. So this is always the case. And then finally, number 5, when we're talking about nonmetals. In their compounds, nonmetals are going to be assigned oxidation states according to this table right here. And this table here has a hierarchy or precedence. So the elements that are higher in the table take precedence over those in the lower. So if you have elements that are, if you have compounds made up of these elements, then if you're going to assign the oxidation states to the ones that are higher first and move your way down. And then whatever's left over is going to get whatever oxidation state they need, right? So for example, fluorine, if it's in a compound, is going to have a -1 charge. So if you have fluorine and hydrogen in your molecule, then you're going to assign a -1 charge to fluorine first for its oxidation state. And then hydrogen will get whatever's left over depending on like how the math works. Because remember, 3 always has to be held. You always have to hold 3 that the total oxidation states of your compound or your polyatomic ion has to equal the sum of the molecule ion. So you have to use that to calculate the oxidation states on any elements that are left over or any elements that are not on the table. So for example, so carbon is not on here. So all of these would take precedence over carbon. So you would have to assign, for example, in carbon dioxide, oxygen would have to be assigned a -2 oxidation state. So since each oxygen has a -2 oxidation state, that means that the total negative of the oxidation state is going to be a -4, right? But the whole molecule is 0 because there's no charge on carbon dioxide. So if the two oxygens have a total of a -4 oxidation state, because each one has a -2 oxidation state, then to balance that out to get 0, according to rule 3, then carbon should have a +4 oxidation state to balance that out to get 0. And that's how that works, right? But carbon, because it's not on the table, just gets what's left over in order to fulfill rule 3. So you're going to follow the order here and assign the oxidation states to your nonmetals that are in compounds according to where they are in the table. So the higher they are, they're going to be assigned first, and the lower ones are going to be assigned later. And if they need to, if you're not on the table or if you're lower on the table, then you're going to be assigned whatever oxidation state that you need. So that's how it works. So these are the rules that you would follow. Again, there's a precedence. These are always positive, so that doesn't change. So if you have metals in group 1 or 2A, then they're going to be always +1, +2. That's if they're part of a compound. So be aware of that. So I hope this is helpful. So be able to use these rules to assign oxidation states to atoms in your compounds. And then once you assign the oxidation states of the atoms in each of your reactants and each of your products, then what you can do is you can look at the individual atoms and say, okay, was there a change in the oxidation state in this particular element from reactant to product? If there's a change, then there was a transfer of electrons, and therefore you have an oxidation reduction reaction. If there's no change in the oxidation states in any elements from going from reactants to products, then there is no redox reaction. Okay, I hope this is helpful. Thanks for joining me. If you like this video, like it, share the video with your friends, make a comment in the comment section. Make sure you subscribe to the channel and ring the bell for notifications for any new videos I put out. Thanks for joining me, and see you next time.